So basically what I briefly mentioned about generative adversarial cleaning, I wanted to show you the basic idea, then you will see much more about this in the tutorial in the third hour, and then I would like to switch to a new topic, which will be the topic of today's lecture. I would like to talk about reinforcement learning. And again, this is a very deep field with lots of results also known from optimal control. I will just give you a very brief introduction to this topic. And of course, there are lots of things to be told. The entire course can be dedicated to this topic. So we want to remind you what we did with generative models. So let me show you just one part of the generative model. We had some latent space Z. And a neural network that we call psi beta. Beta was the set of parameters parameterizing this network that was taking a latent variable Z and producing an instance X in the instance space. Okay? And basically we trained a pair of encoder and decoder. Basically we wanted to create, let's say we start with some X, we then map it to Z by an encoder network, and then we would like to reconstruct, take this Z and take it back to the instance space by the decoder network with the objective to make this distance small. Okay? And in this way, the latent space captured the unknown parameterization of the data. Okay? Now, the fact that we used here a very simplistic distance, basically we used the L2 distance, and we had a probabilistic interpretation, we just assumed some white Gaussian model for the data probability. Basically, we are making some arbitrary decision about the geometry of the instance space. And in fact, if we use the L2 distance here, a very known phenomenon in statistics, known as a regression to the mean, happens when we use the L2 distance. Basically, we might get, for example, if X's are images, we might get something that looks like a blurred image. Basically, something like kind of an average image, which is not nice. We would like to see crisp, sharp images with good, sharp edges, something that characterizes natural images. And using the L2 distance here is not such a great idea to achieve this goal. So the idea that was proposed relatively recently is to basically, let me concentrate now on the generative part, just on the decoder network. Basically, we have latent space. I'm randomizing some latent variable Z, and we basically enforce the data distribution in the latent space to be normal. And basically, I'm training a decoder network that produces me an instance X from the latent variable Z. Okay? And as a result, so let me call this beta. As a result, I will have some distribution, let me call it P beta X. Every selection of the parameter beta will give me a probability distribution function, right? So basically, I will have a parametric family of densities, P beta, depending on the parameters of the network. Then this might be a very complicated density function. Okay, parameterized by that. On the other hand, I have some, again, unknown and very intricate space of real data. This is X, obeying some true probability density Px, which of course I don't know. Right? So what I could try doing, I could create another model, a new neural network basically, that will receive an x. Okay, it will receive an x. Let me call this neural network delta theta. Okay, so it's also a parametric model. And basically, it will produce a probability. It will produce a result. Let's call it. Well, this is basically delta theta of x in the interval between 0 and 1. So I will interpret it as a probability, and this is the probability. So the network will tell me how much it believes that the instance x came from the real data or from a generated set of data. Okay. So basically, you can think of this as kind of an adversarial game. This psi beta, the decoder network, is an imposter trying to forge something that looks really natural, like the real data, and this delta is kind of a detective that tries to discriminate between the forgery and the real data. Okay? So basically, I will feed it both with data sampled from the generative model and from the real distribution. Okay? So basically, like training, I will give it both examples. Of course, since I know which example I'm giving this delta, I can put a label here, and I would like to train this as a binary classifier. Okay? So I'm training this delta as a binary classifier. I'm trying to let's take log delta theta of x. Okay, so I would like this log delta theta of x to be basically I would like this probability to be close to 1, so that log will be something close to 0 if x comes from real data. Okay?
Why do you use log?
Well, this is just a function that is convenient to optimize, because the probabilities might be very small numbers. Okay? Just for numerical convenience. And then I would like this logarithm, let me write 1 minus 1 delta theta x approximately 0 if x comes from the generated distribution. Okay? And so basically, given my generator, I can construct such a discriminator, right? The question?
Yes, it's just a form of logistic regression, small.
Exactly, it's a binary classifier.
Okay.
Right? It has a softmax layer, and basically it's just a regular.
So what we see there is a sort of entropy. I mean.
Exactly, it's a crossover. Exactly.
Okay.
Exactly. So basically, let me write it explicitly. I would like to maximize over theta. So I'm given this generator network, and I would like to maximize over theta. Let me write this just as a single loss function. The expectation over x coming from px log delta theta x plus the expectation. Let me write this expectation over z. Okay, so it's 1 minus log delta theta of psi beta z. Okay, so basically the first term corresponds to the real data that I'm taking from my my instance space x, and the second term corresponds to the generated data. Of course, z comes from the wave distribution principle, right? And I would like to maximize them simultaneously. So this is the forger that forges the data. Let's tune the parameters of the discriminator to be as sensitive as possible to the forger. Okay? But now we can say, given the most discriminative detector, let's tune the forger in such a way that it will reduce its performance as much as possible. So basically, I can put now a minimum here on beta. Okay? So basically, I'm playing this kind of two-player adversarial game. So I'm fixing the forger, and I'm letting the detective to be as sensitive as possible, basically to find the best discrimination strategy. But then I'm making a counter move, and I'm trying to make the forger look as authentic as possible in the eyes of the detective. Okay? And basically, I'm playing this adversarial game. Of course, these kind of min-max problems are nasty to solve, but if you manage to solve it, it really produces extremely good results, and it is a much better alternative than the L2 loss. So you can think of this, if you just think of this max over theta as a loss function for training the generative model, you can think of this loss function as some kind of a moving target. It's not a fixed metric that you are using all the time. This metric always changes as you're updating your parameters better, because this loss depends on that.
But in this method, you only improve the decoder. Maybe the Z is not good enough.
Sure, of course. So I'm showing you just the generative part. Of course, you can also train autoencoders in this way. You can add this kind of adversarial penalty to the loss that is used to train an autoencoder. This is also quite common. Okay? So this is just a way of training. It doesn't impose any restrictions on the architecture of the generative model. It can be a full autoencoder. Okay?
If you want to include the encoder, so beta will include the weights.
Well, you will have beta and alpha, also the weights of the encoder.
Why not with end-to-end?
Yeah, of course. It's just we just parameterize them by two different sets of parameters, but the minimum would be over alpha and beta as well. Okay. And you can combine it with other facts as well. Question?
Can you please remind again the bigger picture? I mean, why we are doing this optimization? I mean, why we are extra training our decoder?
So again, we are interested in producing something that looks like data. We are interested in generating and building a model from which you can sample instances, right? Something that looks like real data. So basically, this is one of useful ways of doing unsupervised learning, right? We would like to discover how the data behave. And one of the ways to discover how data behave is actually to build a black box from which you can generate data. This is called the generative model.
So there are like two parts. The first part is to construct the encoder and the decoder,
Yes.
train it a little bit, and then to check the decoder through this black box, and then doing.
Well, a generative model is just the decoder, right? You can also build a full autoencoder here. We can still take x's here from px, and then put a composition of phi alpha and psi beta as we did with the autoencoder. This is still a valid way to train a full autoencoder. I'm just showing this as a more general setting because you can use adversarial training, and this is how it was proposed to be used just for the generative part of the model. But you can also use it on the full autoencoder. Okay? Okay, so this was the remaining part that I wanted to mention about adversarial training, and of course there are many variants of this idea that really produce impressive results. It's not really clear why it works, but it produces good results.
So,
I mean, from an intuitive perspective, it's quite well understandable, but it is not clear why we don't converge to some useless local solutions of this problem. Yeah.
How can we ensure that the discriminator or the generator doesn't become a more smarter than the other one?
What do you mean?
If the discriminator is much more powerful, then the generator doesn't have the ability to.
Sure, of course. Again, so it is not clear. It is not really clear still. It is from a theoretical standpoint how, for example, a very big difference in the capacity of these two models can affect the result. Right? This is a very non-convex problem that might have useless solutions. But somehow, if you make it work, it produces really good results. It's an ongoing field of research, actually a very active field of research, and some people say that this is just bullshit. This is just memorizing training examples. But I think there is something beyond memorizing training examples. Again, the theoretical sides are quite mysterious, I would say, as of today. Questions?
Yes, please. I would like to take you back to the motivation. So this method will replace the method of using loss function?
Well, so you can think of this part as a loss function. Right?
Yes. So the motivation is to use this method is we get better results sometimes?
Well, basically you get much better results most of the time. So just to emphasize, if you simply use this simple-minded L2 loss, it might not represent well the similarity between images, for example, in the instance space. So basically, the fact that you're using Euclidean distance between 2 points that lie in some manifold, it's a very bad idea, because you might have let's say this is your manifold, and you might have 2 points like this. So if you trust the distance on your manifold as something that bears some semantic meaning, this Euclidean distance is a terrible way to estimate the distance, right? But in order to measure some, let's say, geodesic distance on the manifold, you need to know the manifold, right? But you are learning the manifold, and you don't know which criterion to use in this goal of learning the manifold, right? So it's kind of a bootstrap problem. Okay? So of course, there are ways to geometrically define more meaningful distances, but there are most of the time they are impractical. And using the L2 distances in the embedding space usually is a very bad idea, but it's something pragmatically simple. As a result, you get, for example, generating models that generate blurry images. And GAN's generative adversarial networks is a way to basically essentially to propose a different loss that tries to address this problem.
So my colleague said that you start with, so you have to start with L2, like he said, and then you can go to adversarial.
No, you can train it just like this.
From the beginning?
Yes. It replaces the L2 loss.
So how you get the Z to start with?
Well, again, in this model, Z is just an arbitrary distribution, a sample from a normal distribution, and you train basically all the complexity in generating the instances goes to the model psi beta. So initially psi beta generates random results, and then it goes gradually as you're trying to make it more and more similar to the distribution Px of the real world. Okay? So again, I think it's a cool idea. It's very interesting also to understand it theoretically. It has really made a difference in many fields, especially with images, because images are difficult to synthesize, and also it's very difficult to come up with some axiomatic definition of what is a good distance between two images. So the idea of GAN circumvents this need to define axiomatically a good distance on images. Okay? So I would like to take you to a completely different setting, if you don't mind. Yes?
I have two questions.
Sure.
While training the net, do you need somehow to keep the generator and discriminator equal so one will not overtake the other?
What do you mean? In terms of the capacity of the networks? The size of the model?
If you get too good discriminator, so the generator will not make it to full.
So, for example, if the capacity of the discriminator is too big, it is much more capable on doing fine-grained classification compared to the generative model. It can help. So there is basically some art, some magic in making it work. But if you make it work, it will produce really good results. So I unfortunately don't have any theoretical recipe telling you how exactly to select the two networks. Because frankly, it is not an
Okay. And
unfortunately, there are so many open questions in this field, and this is one.
And another question is it possible to fine-tune a network? Let's, for example, take a network that generates faces.
Mm-hmm.
Will it be possible to fine-tune some features or layers that you can take a model that is already trained and teach it to, I don't know, create dog faces for it?
Well, so if the model is complex enough, if this psi beta is complex enough, and I presume that if it is capable of generating dogs, it should be complex enough and it should be capable of generating human faces. Of course, you will need to train human faces in order to produce something that resembles a human face, right? But again, basically, you usually in generative models you usually put quite big models that are capable of generating everything, right? And it's just a question of how much you train it and how many data points that distinguishes between success and failure.
But if you have, I ask it because if you have a very large data set of faces, human faces, and a very small data set of dogs, if you can.
Okay. So basically, probably your question probably let me refine it and tell me if this is what you mean. You are asking how to make use of knowledge acquired on some different task and transfer it to a new domain, right? So we will say a few words about transfer learning, let's say, or domain adaptation, domain alignment, how to make use of knowledge in one task to better solve a different task. For example, to be able to train a new task on a much smaller amount of data. Like, for example, probably an extreme example would be some kind of zero or few shot classification. So you have seen 1,000 classes of images, and now I'm giving you one example of a new class that you have never seen, and now you need to train a classifier using just one example. Okay, this kind of problem that probably you're referring to, right? And there are interesting ways of doing it. Again, it's a very active field of research. Okay? So we'll probably have time to address at least a few bits of these problems. Yes?
Regarding the distance between images, I mean, if we have a latent space,
Sure.
can't we compute distance in the latent space? I mean,
Of course. So we can do many things in the latent space, and actually we can do also arithmetics in the latent space. We can manipulate vectors, right? But you are using the distance to train something that takes you from the latent space to the instance space, right? So you need that distance in the instance space to train the model, basically to make the latent space useful, right?
but here you're not modifying the encoder part. So let's say you have an encoder.
Sure. But so in this setting, I don't have an encoder on top. So I just have the generating part. Okay. Still, this maps from something arbitrary in the latent space to something very intricate in the instance space is exactly my generative model, right? It can be extremely complex. This psi beta might be a network with millions of parameters, and it might model very complicated density functions, right? Yes.
So if we claim that the Accelerators actually projects onto our mounted manifold, so is Z while training is just random, could be random noise or
Well, so usually, when you use a generative model, Z is a random noise. You basically you feed it with random noise, and it gives you, let's say, human faces.
okay.
So basically, every random realization of this input will give you a different point on the manifold. So think of Z as kind of coordinates on the manifold, right? But you always stay on the manifold. So you just sample it at random places.
And it should be N01.
What is N01?
Last time we imposed.
So again, we have this flexibility of demanding some single distribution on the latent space, because basically any transformation between the distributions can be absorbed into the model side there, right? And then we choose something simple. Doesn't need to be Gaussian, but Gaussian is something that is easy to do. Okay? Okay, so let me now take it to a different end. So basically, until now, we essentially talked about two kinds of learning settings. So one was supervised learning, in which we tried to regress, basically tried to discover a map between some input space and some output space, between our instance space and our label space, based on input-output pairs, examples of input-output pairs that were given to us, right? And basically we formulated supervised learning problems. Then we turned our attention to the unsupervised setting. In that case, we don't have a map from X to Y. We had just some latent data distribution, and we wanted to discover, to capture it with some succinct, some compact representation, right? And that was basically our latent representation being unsupervised. So let me now show you a different setting, which is very, very common, and actually probably you can say that this is probably the closest you can get to using machine learning in artificial intelligence kind of problem. So basically, we have some kind of an environment. Environment is just a huge state machine. If you believe that everything in the universe is computable, then it's just a big state machine. And then we have some agent. Okay? So the agent can act upon this environment and change its state. Okay? And so the environment is a state machine. It receives an action from the agent. Let's call it AT, an action at time t. So there is a certain set of actions that we can perform in the environment. It receives the current state ST. Okay? And it produces a new state ST plus 1. That's exactly a state machine, right? Basically, it takes an input, takes the current state, and brings the state machine into a new state ST plus 1. And then I will be assuming that t is a discrete time variable. Of course, we can run it in continuous time, but then things will become more complicated to treat mathematically. And one important thing, the environment will also produce a numeric reward signal, which I will be denoting by RT plus 1. Okay? There are many ways to define this reward, but basically I would like to train this thing. I'm also assuming that the state is fully observable to the agent, which might be a reasonable assumption in some problems. It is a completely unreasonable assumption in some problems. Like, for example, if you're driving a car, you don't really see what is behind the curve. So maybe the environment knows exactly what happens there, but you don't see. So you don't fully observe the state of the environment, and there are extensions of the theory that I'm going to show you to the partially observed case. For simplicity, we are not going to do. And basically, people in reinforcement learning just assume full observable state, apply this machinery to all kinds of problems, and quite successfully. Okay, but of course, the theoretical treatment has to deal with partial lack of observability of the state. Okay? So again, let me formalize this. I have some set, let me call it like this. Set S is a finite state space. This set of states. We can make it discrete and infinite, but again, for simplicity of the treatment, let's make it finite. And this state, of course, depending on the game, so let's say we have a chess game, right? So the state of spaces will be all the possible combinations of the location of the pieces on the board. It's a huge state space. It's discrete, it's finite, but really infinite for every practical purpose. Or if, let's say, we play a video game, the state of the game would be all the possibilities of the pixels displayed on the display. Also, quite a huge state space. Then we have a state of actions. So let's say if I'm driving the car, this is what these are the controls I can give my car and consequently the environment. Or if I'm playing chess, these are all the possible moves I can make. I can restrict the set of actions to the set of actions accessible from a given state. But again, let's keep the thing simple. Let's assume that A is just a set of actions. I might perform every action, and some of the actions will simply not affect the state of the environment. For example, if I'm playing a Pac-Man game, there might be some moves that are impossible in certain state mode, and basically I just wasted my move. Okay? So this is the set of action. Now I will have some. So basically, I will be modeling by ST the current state. And basically the environment will receive the current state, will receive the current action, and will produce a new state. Okay? And this will happen, at least in the general setting, this will be some kind of a stochastic transition. It doesn't necessarily need to be deterministic, and the transition probability is essentially the probability of a new state ST plus 1, given basically all the previous states and all the previous actions. Okay? So this is my transition probability. So this is the history of the process, and based on this history, this is the probability of reaching a new state ST plus 1. Okay? Now, to simplify treatment, actually to greatly simplify treatment, I will assume what is called the Markovian property. So the Markovian property simply tells that the conditional probability of the new state, conditioned on present and past history, only depends on the present and not on the past. Okay, so essentially, it means this, that I can only condition on ST and AT. So current action and current state, this is the only, these are the only parameters that influence the probability of getting to a new state. Okay, and not the entire past history. Okay. A question is?
What could possibly lead him to such an assumption or philosophy? I mean, why is this right or attempt to be right?
Well, it's not right or wrong.
Or
It's
just-
you can come up with games that do not satisfy this property, but if you take many games like chess, for example, so basically, let's say, or maybe chess is not a good idea, but you can think of many games where basically, if the environment is modeled by Markovian state machines, essentially, then you don't really care about what happened in the past. You only care about your state in the present. Of course, you can engineer many games where this problem is not satisfied, but this is a pragmatic assumption. It's much easier to treat Markovian processes as opposed to some more general processes, because then you don't have a simple tool to define transitions. I will make another assumption that might also be not necessarily true.
It works for chess as well.
Pardon?
It works for chess as well. You don't need to.
Well, it works for chess as well, but basically, chess is a deterministic, right?
Yeah.
Well, but I was looking for some more interesting example. Let's say blanket, or something like that. Something that has some randomness. So basically, all these are Markovian processes. But I would like to make another assumption. So this is the Markovian assumption. This is the Markov property. I would also like to assume that this transition probability doesn't depend on time, that it is shift invariant in time. Okay? So the probability of transitioning from state ST under action AT to state ST plus 1 is exactly the same probability as transitioning from AT plus delta, from ST plus delta under action AT plus delta to a new state ST plus 1 plus delta. So basically, if you shift your gain in time, this transition probability will be exactly the same. And then I can say, so this is basically time invariance. Then I can say that I can simply encode this transition probability by P of S T plus 1 equals S prime, given ST equals S and AT equal A. Okay, and I will simply specify this transition probability PS prime given SA without specifying the time.
Which is S prime now?
Pardon?
S prime, what is standing for?
S prime is just a value of the state. But basically, I would like to write the function like this without specifying the time. So it's the probability of transitioning from current state S under current action A to future state S prime. without specifying at what time. So it's in one step, but doesn't matter if I'm doing it in the beginning of the game or after million steps. Okay? So this is the time invariance property. By the way, time invariance property doesn't mean that the process is stationary. The process might be extremely non-stationary. Stationarity means that the entire joint probability of all the states of the process is shift invariant with time, right? And this is just the conditional probability. This is just the transition probability. The transition probability might be time invariant, and the process might be non-stationary, right? See the difference? No?
No, the last sentence you said about time invariance, I agree and I feel comfortable with it.
So stationary process means that if you take any set of time samples of the process, let's say state at t1, state at t2, state of tn, you take the joint probability of these states, and now you take the joint probability of the same states with the same time differences, but now you shift them by an arbitrary time shift. If the probability stays invariant to this shift, the process will be called stationary in a strict sense. Okay? But the fact that the transition probability is shift invariant doesn't mean that the joint probability will be shift invariant. So, for Markovian processes, there is a very simple property that can be verified. Basically, you need to initialize the process with what is called a stationary initial distribution in order for the process to be stationary, right?
So, for example, if I take one snapshot of a situation and I move it in time, so the probability for some event is the same.
Well, again, so here I'm treating that just the transition probability, the probability of getting from one state under an action to a new state. Okay?
But taking a set of these steps.
So the probability of observing, let's take the marginal probability. The probability of observing a certain state at time t might change with t. Okay? So the process is not stationary, but the transitions are time invariant. Okay? Okay, so basically this will be my process. And I'm missing a few important ingredients here. Okay, so the next ingredient that I would like to define is the reward. So I will assume that I have some function r as a. This is the reward. This is a deterministic reward that is given for applying action A at state S. Okay, and by the way, in real games, reward might be stochastic, then this would be the expectation. Okay, this is the expected reward. Let's call it instantaneous or immediate reward. Okay, so this is the immediate reward that I'm getting for doing a certain action in a certain state. Okay, and of course, immediate reward is not something that is extremely useful. So for example, if I'm playing chess, the real reward that I care about is whether I lose or win, right? And this happens after many moves. So that reward is delayed by a certain amount of steps. For example, I might be getting a negative reward for every step that I'm doing because I want to win as fast as possible. But basically the major impact on the total reward, what is called the return of the game, is somehow counting all the possible, basically all the rewards, all the immediate rewards. So basically I will define by RT the immediate reward at time, let me call it t plus 1, RS AT. So basically the environment is currently at state S, I'm executing action AT, and the environment transitions to a new state ST plus 1 and produces a reward that I will be labeling as RT plus 1. Okay, so this is the reward for action AT. Okay? And I can simply sum for k from 0 to infinity RT plus 1 plus k. Okay, and call this my total return. This is the total return of the game. Okay? The problem with this is that this is usually going to be infinite. And it's very difficult to treat something that is infinite. For example, I will not be able compare between different policies, different sets of actions that I can take, because all of them will produce the same infinite total return. So what I should do probably, the question is?
The total return is beginning from some time.
Yes, so let me write it as G. Okay, from the current time until the end of it. Okay. So basically, this is something that I cannot treat. So basically, one of the standard ways of treating total return, I will simply limit the horizon here to some finite n. So this is called finite horizon definition of return. Another way is basically to introduce a soft version of horizon. I will be just discounting with exponentially decaying function the future returns. And this is something that is very tractable. So instead of putting a limited horizon here, I will simply put some discount factor here and run k to infinity. And this gamma will be some fixed parameter from 0 to 1. Okay? This is called the discount factor. Okay? So basically with this discount factor I can define finite returns. Actually, if your immediate return is bounded by some constant, then your cumulative discounted return will be bounded by that factor over 1 minus gamma, right? It's a finite number. Now, basically we have all the ingredients. We have basically the following tuple. We have S, that's the space of all possible states. We have A, the set of all possible actions. We have our transition probability, P, that we assume to be Markovian and time invariant. We also have our return, we have also our reward function R, and we have the discount factor gamma that defines the total return. And basically this tuple with these 5 ingredients is called a Markov decision process, or MDP.
You have a small problem when gamma equal to 0.
Well, if gamma, what is the problem of gamma equal to 0? If gamma is equal to 0, then you only care about your immediate returns.
K equal to 0 also in your equations.
Okay, so if gamma equals to 0, then all the tail will be 0, except for k equals 0, because 0 to 0 is defined as 1.
Yes.
Okay? Okay, so basically this is called the Markov decision process, and essentially think of the Markov decision process as the rules of the game. So basically, this set of mathematical objects define how the game works, how the world works, how it responds to the actions of the agent. Okay? And basically, and here is probably the fundamental difference between optimal control and reinforcement learning, so except the fact that basically these two very much overlapping fields is worked on by different communities of people who hate each other and don't talk to each other, except that basically in control, you usually assume that you know the MVP. You know the underlying environment, you know the system, and then you would like to define some optimal policy according to which you make your agent behave. Usually in learning problems, the environment is unknown, and you need to learn it together with learning the optimal policy. Okay? And this is more or less probably the main distinction between the two settings that you can think of. But otherwise, the formalism and the tools are quite similar. So basically, you can think of probably a few more important observations. So you cannot. So you basically learn. You can hope at least to learn something by playing many games and failing many times, like in life.
Are you able also to learn or to extend your domain of actions? Let's say you start by thinking, oh, I can manipulate only by, say, I don't know, 2 stuff, or then, and then as you go, you might be able to extend it, like a baby that
Sure. So I'm assuming that A are all possible actions that you can act upon the environment. So maybe you are unable to perform some actions, or some of them are inaccessible. So that is a different story, right?
And then also your observability and your
So I'm assuming full observability of the state of the environment, which is of course not very realistic.
maybe
It
not
makes
expense.
treatment simple. Otherwise, you need to deal with partial observability.
Do we have any intuition or a way to find the best discount factor?
No, it's assumed to be a parameter of the problem. But you will see that we are not going to necessarily depend on it so much. So it will be a meta parameter in the problem most of the time. But there are ways to absorb it into one model or another.
Can we loosely compare this gamma factor to the motivation journey? I mean, does this gamma imply some sort of motivation? Because if it decays exponentially, so I tend to see it as a game, and I'm playing the game, but as long as the game runs and I'm not winning yet, so I'm getting more frustrated.
Well, with gamma, you can think of gamma as some kind of memento mori, right? Some kind of basically remembering that life is fine, right? So basically, you don't really care about reward in 1 million steps. It might be huge, but you might not survive. So that's why you are discounting remote future.
So it helps us actually to achieve faster results.
Well, not necessarily faster. You might get suboptimal results in the long term, but it tells you to prefer something that you get some kind of immediate gratification rather than postponed gratification. So basically, the exact value of gamma tells you how much immediate gratification you prefer over postponed gratification. Okay. So again, it's a parameter that you need to set. Yes.
How do you handle it?
Yeah.
So, how do you handle if S or A are not discrete? Like reinforcement learning on walking.
Sure. So there are extensions to continuous states and probably more interesting continuous actions. So it's basically like the difference between classification and regression problems. So you will see how we treat basically the actions in the actual learning problem, and you will see that at least technically it is not so difficult to accept. Okay? Question? Yes.
Is there a benefit sometimes to somehow see, okay, I may not be able to observe everything, so train in parallel another agent, and then you might be able to, it's like either to clone yourself and have other than obvious parallelism you might get to observe better,
Well, again, there are basically extensions of these MDP formulas to what is called partially observable MDP, which handle this partial observability, but again, we don't have enough time probably even to deal with the basic setting, right? So let's keep it simple. Of course, it is not super realistic in the real life situation. Okay. So one more thing that I wanted to mention is basically that you, in order to be able to learn efficiently, you need to fail many times. To fail and to win, of course, many times. And this means that you cannot really cope with infinitely long games. So basically, an infinitely long game that doesn't give you some reward when you win or when you lose is something that is not really easy to learn from. So you would like to define some states, some values of the state that we will call terminal states. So a terminal state means that game is over. Either you're dead or you won or something else happened. But basically some states will be terminal. And then we have what is called an episode. So you have some initial state S0, you act upon it with action A0 and you receive a reward R1. Okay? And you transition to state S1. Okay? Then you again act upon this state by action A1, receive reward R2 and transition to state S2. And this happens until you you are found in a state st minus 1, act on it with action at minus 1, receive reward t, and you go to state st, which is game over. And then the game finishes. And this entire trajectory is called an episode. So this is an episode. At least this is called episode in the learning community terminology, and the subsequence, basically a subpath in this trajectory is called an experience. And I will call an experience basically this transition. So basically you are in a certain state, you act on it with a certain action, you receive a certain reward, and you transition to a new state. So this is your experience. Okay? And you collect many experiences as you learn. Okay? So this will be a single, the most basic unit of experience. Okay? Okay, so let's do it. Okay, so basically we created this formalism. We think of trajectories through our space of states and actions. Basically, let's say this trajectory tau. These are basically episodes, and subsections of these, sub-portions of these trajectories are our individual experiences. So basically this defines the rules of the game. That might be deterministic, there might be unknown. Basically we might want to learn them together with the behavior of the agent, but let's now formalize the behavior of the agent and its quality in the sense of the return that we define. So the behavior of the agent will be totally described by what is called the policy. And I will denote it by pi a given s. And pi a given s will be simply the probability of taking action A from state S. Okay, and since we are assuming that that basically we have time invariance, I am not specifying t in the definition of the policy. And again, this is a conditional probability density, probability distribution, right? So basically, it tells me for every action A, given a state S, what is the probability of this action A, right? This is a conditional probability.
But A is the action that you choose to take.
Exactly. So this generally describes as stochastic policy. So I will draw an action from this distribution, right? So I'm currently at state S, and I'm drawing an action from this distribution, right? So action time t will be drawn from this distribution. Okay? And if in a particular case when the distribution is a singleton distribution, it will correspond to a deterministic policy, right? If it has probability 1 of selecting a certain action and probability 0 for all the rest of the actions, this will be a deterministic policy. And this is basically a more general model that allows stochastic policies as well. Okay? And it will be easier to treat mathematically. But of course, it's a superset that includes deterministic policies as well. Okay? So now, once we have the rules of the game and the behavior of the agent, let's try to predict the return of a specific policy. Okay, so we want basically, first we would like to predict the benefit of a given policy, and then we will try to optimize the policy to maximize this return. Okay, so basically it's the problem of predicting the performance of the agent and doing optimum control.
Alex, before you continue this question, in game theory, usually you try to reach the equilibrium point, some balance point between. Here you try to optimize it to the optimal. Do you have any similar notion?
Well,
we will in learning.
We will have this notion that corresponds to basically ideas in multi-criteria optimization, where basically you have multiple criteria, So we have basically a value function that depends on the state. And we would like to improve this value function for all states. Right? So it's kind of similar to Pareto optimization. Right?
Okay, let's
Multi-complete. But so basically, let me define what is called the value functions. We generally define two types of value functions. There will be a state value function. So a state value function tells me the value in the sense of this discounted cumulative reward, basically the total return of the game, the expected return in the game. There we put an expectation operator. If I start at a certain state S and then continue playing according to some policy path. Okay? So basically it will be a function that I will be denoting by V, depending on the policy pi, obviously, and depending on the state with which I'm starting. Okay? And again, this will be the expected value of GT conditioned on ST equals S. This is my starting state. And of course, conditioned on my policy pi. Okay? And I will show you in a second the exact spelling out of these expectations. They are just computed as a normal Markov chain. Okay? Now, well, let's write it explicitly. We don't really care about the specific time, right? So I can write it as the expectation of t going from 0 to infinity of gamma t rt plus 1 given S0 equals S and time. Okay? Now this is the state value function. It tells me the under the given policy pi, what is the expected reward if I start my process at state S. I can also define a function, a value function that starts with a state and a specified action. So I have a state action pair, and this is called an action value function. And it is denoted by Q pi S and A. And this is again the expected return. Let me write it explicitly. Given S0 equals S, A0 equals A. So I start at state S. I first perform action A, and then I continue according to the policy. Okay? And this is the action value function. Okay? So let's do some algebra on these value functions and see what we get. So let's start with the state value function. Okay? So the state value function pi v pi s. Let me write this explicitly. So it will be the expected value of R1 plus gamma R2 plus gamma squared R3 and so on from S0 equals S given pi. Okay? So let me write this as the expected value of R1 plus gamma times R2 plus gamma R3 and so on given S0 and pi. Okay? Now what can you see here?
Of course. That's the other thing.
So this is also V pi, right?
It's a recurrent.
Yeah.
From S1. Right? Basically it starts from, of course, from state S1. So we'll write it as the expectation of R1. Why was it R1? It's R0, sorry. No, it's R1 plus gamma V pi S1 given S0 pi. Okay? So basically, the question.
I think without taking the expectation, it is only G1, and after taking the expectation, it becomes V, pi at S1. So it should be maybe G.
What is G?
You define the G, the return.
G is the sum.
You have the return, which is a random variable, and after taking the expectation, you get
G. So it's basically it's return starting from time point 1, right? So now let me write these let me write this expectation explicitly. I will write it. I will write it there. Okay. So let me write it explicitly. V pi at state S. Okay. So the expectation goes over all possible actions, right? So basically, I'm currently at state S0, right, equals S, and I can take all possible actions from the action set, right? So I will write an action from A, and the probability of taking that action from state S is exactly our policy, pi, A given S, right? This is the probability of taking that action. Now, once I have taken this action, my immediate reward, which is the first term in the expectation, so this is immediate reward plus future reward for all subsequent steps, right? So my immediate reward is simply this function R, will be noted by RSA, right? This is the immediate reward of playing action A from state S, right? This is part of our MDP. This is part of the rules of the game. Plus, now here, I have basically, what is the expectation of the future? The expectation of the future, I will now, of course, discount it by gamma, right? Basically, I can now, from this point, I can transition to one of the possible states in the state space, right? So I will have some sum over S prime in the state space, right? And the transition probability is given by Ps prime given S and A, right? This is my transition probability. And then basically what is written afterwards will be simply V pi of S prime, right? This is the future value function at state S prime. Okay, so let me write it like this. Let me write it as sum over A of R S A pi A given S. Okay, and the sum is over this variable A. Okay? Plus, let me write it like this. Let me write it as sum over S prime in S. Sum over S prime in S, sum over A in A of P S prime given S A pi AS times V pi S prime. Okay, so here internally I have a sum over A, and then externally I have a sum over S prime. Okay, so this resembles matrix and vector multiplication, right? So I can think of so if I have a finite state space, I can write a vector V pi, which is V pi at some state 1 until V pi at some state n. Let's say I have n states. Okay? So I have n possible states, in which n might be a very big number, but it's a finite set of states.
How did you lose the gamma?
Yes.
Of course, with the gamma. Okay? Obviously with the gamma. So basically, if I think of V pi as a vector, what is written here is also a vector depending on the policy. Let's call it R pi. And what I have here is a matrix, depending on the policy, right? It's a matrix, right? You see, basically, the matrix has a coordinate s, right? And it has a coordinate s prime, which is the second coordinate according to which I'm summing the elements of this vector, right? So I can write this as v pi equals r pi, so both are vectors, plus gamma p pi v pi. Okay? And then of course I can simply solve for v pi to be I minus gamma p pi inverse times r pi. Okay? So basically, like, given a policy, I can actually solve for the value function. Okay? And if you don't like to invert matrices, you can actually do what is called a fixed point iteration. I will show you the fixed point iteration in relation to optimal policies. Okay? So basically, this is the state value function that tells us the expected value, the expected return, if we start from a state and act according to the policy path. Okay? And we can do the same, exactly the same thing with the action value function, q pi. Let me just write the final result. It's exactly the same thing. So basically, this is the value function of starting with state S, performing an action A, and then running the policy. So it will be simply given by, again, the instantaneous reward RSA plus gamma times sum over S P S prime given SA times sum over the actions A prime these are the next actions by A prime S prime Q prime S prime A prime. Okay? And again, the derivation is exactly the same as we did with the thing. And of course, the relation between the two functions, again, this is this is straightforward to obtain. So what is exactly the value function at pi? Basically, given so we are fixing the policy pi. What is the value function? What is the value function of a state S? How can it be expressed in terms of the action value function?
The full probability.
So basically, it is the probability over all the possible actions I can take in this state. The probability of the actions are given by the policy, right? Times the value of these state action pairs, right? Very simple. Okay. So basically, now we learn how to predict the value of a given policy, right? Either if we start with a certain state or if we start with a certain state and action pair. So basically, we know how to predict which policies, basically. So each policy will correspond to a trajectory, right? So if we have a certain policy, then we start with some state S0 and we generate a trajectory. So from the starting state until the end of the game, right? So we have some tau, right? Some trajectory tau, and we can associate each trajectory a value function, right? So basically, because the game in general, the policy is stochastic, we might have different realization of these trajectories under the same policy, right? And we would like to select a policy that gives trajectories with the best reward, with the maximum return of the game. Okay? So basically, we would like not only to be able to predict how well the policy performs, but actually to optimize the policy with respect to this return. Okay, this brings us to the problem of optimal control, or optimal policy solution.
you said that the policy is just a sort of a big matrix, right?
Well, so it's a matrix. It gives the probability for every state and every action, right?
Yeah, so it gives this it gives a distribution for every state, what actions it will take, right?
It's basically it's a discrete distribution, right? Because we're
Yes.
assuming that we have a discrete state and action space. It can be captured by a matrix.
Okay, but
It's a conditional probability, right?
yeah,
So
yeah.
basically, in one index you have the probability. So basically, every column is a different type of condition.
Yes. Now, the thing is that a policy seems, for me, much more complicated than. I don't know. It seems to me that we don't have enough information because.
Right.
Huh?
You can do amazing things with this simple model.
Just with it being a matrix of different distributions on each column.
Sure. It might be something. It might be very big, right? So basically, this value q. So okay, so I will show you that you can actually find. You can find and mathematically prove, first of all, the existence of an optimal policy and actually show how to find it. But this will be impractical because this function q, or this function v, if the state space, for example, in chess, the amount of possible combinations of pieces on the board is really huge, right? So basically, evaluating, so if you know how to evaluate this function for every possible state and every possible action, then you know how to solve the game. You can really play optimally. You can find a mathematical derivation of an optimal policy. But practically for chess it is impossible. Because the state space is practically infinite.
So there is
it's
no
finite, but it is huge.
Yeah.
So what we will have to do, we have to approximate this function. And this is where deep learning enters the game. Because we will use a neural network to build an approximator to this function. Okay? And we are not, and unlike control, this is another point of divergence between optimal control and learning. Basically, unlike control, we will really care about approximating this function well in those parts of this space where we play common. And some rare situations, you might perform really badly in those. Okay, so you would usually not afford such a thing in optimal control, because you want basically some guarantees that, for example, the system will not crash under any reasonable circumstance. And in learning, you usually don't care. You discover the rules of the game together with learning the optimal policy. Okay?
Together with what?
With the policy, with the optimal policy. So let's do this. I would like to show you how to find the optimal policy. Let me define. So let's take a value function, a state value function. A state value function will be denoted by u. It is some state value function resulting from a policy that assigns every state a number, right? This is the state value function. It is of course parameterized by a policy. So let me define an operator that I will call a Bellman operator. Not sure if this is a common name, but let's call it a Bellman operator. I will be noted by T. So TU, an operator basically takes you a function of this form and then gives you another function of this form. So basically it's an operator on state value function. And I will define it by specifying, so this is a new function. You can call it V. So the operator maps from U to V. And I will specify that every state S. Okay, so at every state S, the operator will give me the maximum over all possible actions A of R S A plus the sum basically discounted by gamma. Okay, so I hope you agree that this is a valid operator to define on the space of state value functions, right? And I will show you that it will lead us to an optimal policy. Okay. Now I would like so this is one construction. Basically, you see, when they write it. So you see, basically, I had this expectation written here. Basically, I was summing over all the actions A. So now, instead of taking expectation, I will maximize over A. I will take the action that maximizes the expression that I previously had under the expectation. Okay? So basically, this is what the Bellman operator does. It takes a value function and does this maximization. Okay? Now, I will also define a deterministic policy in the following way. So you are giving me a value function, u, and I will define some deterministic policy that I will write as pi star u. Again, a policy is a function that accepts a and s, so I will define it as a function of a and s. It is deterministic, meaning that it will give a singleton conditional distribution. Okay? So it will be 1 if A is exactly the maximizer of this expression. So if A is argmax, let's write it over alpha from A of Rs alpha plus gamma S prime and S, Ps prime given SA, US prime, and 0 other one. Okay? So you see, basically, you are giving me a value function, and I'm constructing this deterministic policy that presumably does something good. Okay? Okay. So, so basically, I can, if you are giving me a policy u, okay, if you are giving me a policy u, sorry, a value function u. So the value function. So we know how to compute a value function from the policy, right? Now I'm telling you how to compute a policy from a value function. Okay. So if I'm starting with a value function u, okay, and I'm computing this particular policy pi star u, according to the rule that I wrote. And then we compute a value function that is associated with this policy that I constructed. What I'm claiming is, what will be this value function? Pardon? It will be t applied to it. Okay? And you see basically that these two things are related, right? So this is the maximum, this is the argmax. Okay? So what I'm saying is that I constructed a policy in such a way, I constructed a policy from u that will give you a new value function that is given exactly by this. Right? Okay. So what I'm going to do next, I will start from some arbitrary value function or some arbitrary policy. But basically, this fact is quite easy to show, right? So another fact that is relatively easy to show, that Tu will be no worse than U, in the sense that for every S in the state space, Tu at state S, Tu at state S, which is the value of Tu, if we start from state S, will be non-inferior to the value of the original U at state S. Okay? So basically, by doing this step, by applying T to U, which is essentially constructing this deterministic policy and the resulting value function that is derived from it, basically, or equivalently by applying this operator T to U, I'm improving my policy. Yes, sir.
This inequality is element-wise?
It's element-wise, of course. So basically, when I'm writing here, I imply this. Okay? It's an element-wise element. So I didn't deteriorate the value function at any step. Okay? So basically, doing this step is a policy upgrade, policy improvement in the sense of the value function. Okay? So now we know that our reward is upper bounded, right? So basically our total expected return is upper bounded. If we have some maximal instantaneous return, let's say of some big number R, this cumulative discounted return will be will be upper bounded by m over 1 minus gamma, right? This is the sum of the geometric series. So we have, basically, we have a monotonic sequence. This is a monotonicity property. We have a monotonic sequence. I will apply my operator n times to some initial u. So this sequence is monotonic, right? We are always improving our policy, and it is upper bound. Okay? So from this I can say, and I'm a little bit sloppy in the math here, but I can say that it will converge to some limit point that I will call V star. Okay?
Why it's upper bound?
Well, because you don't have infinite rewards. The way we define this discounted cumulative reward.
Because we choose a gamma?
Well, exactly. We choose gamma smaller than 1, strictly smaller than 1. That's why I insisted on it not being 1. Right? And I'm assuming that immediate rewards cannot be infinite. Okay? So basically, I have this convergence to a limit point. Another thing that is also straightforward to show, if you examine the limit exactly, you will see that actually this limit point is the stationary point or the fixed point of P. So basically, P V star equals V star. Okay? And this is a very simple property to show. So basically, now we have a recipe how to find the optimal value function and therefore the optimal policy, right? The optimal policy comes from here. Actually, I shouldn't be saying the optimal policy because I'm not guaranteed any uniqueness. There might be optimal policies that achieve the same value function. And one of them is this deterministic policy. So basically, I'm guaranteed to have a deterministic policy that is optimal, but there might be some other optimal policies as well. This is quite natural. Same way I might have multiple stationary distributions in the Markov chain. So let me now write explicitly. Let me now write explicitly this basically fixed point equation. So basically, I will write. Okay, let me write it. V star at state S has to be equal to P V star. At S, I have P written there, so it will be equal to max over A. R S A plus gamma sum over S prime P S prime S A V star S prime. Okay?
What are we doing now?
Well, I'm just writing optimality conditions. So let me write it like this. This is equals V star S. Okay, let me put the box here and call this by name. This is called Bellman's equation, or Bellman's principle of optimality. So basically, it tells us an equation that an optimal value function has to satisfy. Once we have the optimal value function, we of course can compute immediately the optimal policy. Okay? Since we know how to solve, and we know how to solve this equation, right? We just do fixed point iteration. We start with some v0, right? And then we improve it by writing that vn plus 1 at s equals max a in the set of fractions r sa plus gamma sum over s prime ps prime given sa vn s prime. Okay, so this is a fixed point iteration. It should converge to, it will converge to v star at s as n goes to infinity. Okay? So essentially, what is the meaning of this of Bellman's principle of optimality? So basically, it breaks down the problem of finding an optimal policy to two sub-problems of finding one step, basically one action, so one step in this optimal trajectory, and solving for the optimal policy for the remaining part of the trajectory, right? And basically, this equality tells us essentially that when we are doing an optimal selection of the policy, the action that we are taking and the policy that governs the rest of our actions should be optimal for the rest of the decisions as well. Okay, so basically, once we did our optimal step, the remaining steps, basically the remainder of our actions also should be an optimal policy. Okay, and basically we encounter Bellman's name in everything that has to do with dynamic programming, right? And basically this fixed point interaction is known as dynamic programming. Okay, this is probably the most general form of dynamic programming. We can certainly think, probably we imagine it in programming applications like coding, like the Derby algorithm, or maybe finding shortest paths in graphs. But this is a more general form. You can also think, if you think of shortest paths in graphs, basically Bellman's optimality tells us that if we have a shortest path, then basically we can segment it to a path from our initial point to some arbitrary point on the path, and then from that point to the end point, and the two subpaths have also to be shortest path. If not, we can find a shorter path and basically just concatenate these two shortest paths, and we get a shorter path, which of course contradicts the optimality. And we get exactly the same story here. So if either of these sub-problems is not optimal, we can find a better policy, right? So basically, and I see that I'm running out of time. So basically, this tells us a recipe on how to find the optimal policy. We can do exactly the same, by the way, with the Q function. So let me just write it for completeness. I will write the Bellman's equation for the Q function. Q star SA equals RSA plus gamma. We have basically the maximization. We have the maximization in the last part. So you see, again, basically this optimal form that satisfies the Bellman equation has replaced expectations with maximum over there. Okay? And the optimal policy actually has a simpler form in case of the Q function. So pi star A given S. It's also a deterministic policy. Again, it will be given by the arg maximum of this, right? So basically, if we take an action A, we take an action if A equals to the arg maximum over some alpha in A is Q star alpha S and 0 otherwise. Okay. So basically, this is our optimal policy associated with the optimal Q function. So in case of V function, we need to do one look ahead, right? Basically, we need to evaluate this R maximum of the instantaneous reward plus the future reward. And in case of the Q function, we just take the R maximum of Q star with respect to A, with respect to the action. So basically, if Q star gives us the expected return of taking an action A from state S, what is the best action, which essentially the policy, right? What is the best action to take from state S? Is the one that maximizes Q, right? And you can easily prove that basically these two views are equivalent. Then basically the optimal policy written here and the optimal policy written here will give us exactly the same policy. They will give the same state value and action value function. Okay? And there might be other optimal policies as well. Nothing very uniqueness, but this is one of the optimal policies. Okay.
In this process, pi won't become deterministic because it chooses only 1 and 0 for each specific action?
Yes, so basically we take an action that maximizes Q, right? So it's the deterministic selection. If we have more than one maximizers, we can take take, we can define them.
So pi becomes deterministic and not
Yes.
by formula.
So we can say that there exists a deterministic optimal policy, right? There might be also stochastic optimal policies.
Okay.
Okay? And basically, this is again a recipe how to find it. You do this dynamic programming. You can do either this or this. Of course, you can write a fixed point iteration. Sometimes it's called value iteration. You can also write a fixed point iteration of this, right? But the problem that for small games it is fine. For example, if you want to play tic-tac-toe, actually try doing it on paper. You can solve this dynamic programming problem for tic-tac-toe with, let's say, a 3x3 board. It's a very small state space, and finding the optimal policy is easy. But if you, for example, play chess or Go or any practical real-world game, the state space usually will be huge. So solving this is completely infeasible. Even though it is possible in theory, it is not possible in practice. So what we are going to do, we are going to, and we'll tell you about this next week, or actually in 2 weeks, because we have vacation next week. So basically, we are going to replace this function q star by some approximator, and we'll put a neural network here that will approximate the value of a given action from a given state. Okay, and we'll learn it. We'll explain you how we learn it. But basically, this will define basically these approximations to dynamic programming give rise to what is called reinforcement learning. And there are two ways of doing reinforcement learning. Basically, we can approximate Bellman's equation, so we can look for a parametric form of Q that will be trained in the supervised regime by using basically this expectation as the supervised signal. So basically, we would like Q that approximates the Bellman equation in some least square sense, for example. So this is one possibility. Another possibility is to write the value, is to write the expected return for a policy and actually parameterize the policy itself. So put a neural network that parameterize the policy. Okay, so these are two different approaches, and you will see that actually we can combine them into a sort of a hybrid method that tries to optimize policy, which is called an actor-critic architecture. So we optimize policy, so we find the best actor, and then we also optimize over the value function of the critic that tells the actor how well it performed. Okay, so this is a combination of both approaches. We'll see them next time. Okay.